This is some advice on how to complete the exercise of writing a short scientific paper entitled Determination of the Extent to which Coastal Waters are Contaminated by Drainage from Paris Mountain, Anglesey, UK. First of all, we have to write an introduction. The role of the introduction, first of all, is to justify why the work needs to be done. As you get further into the introduction, it should meet the need of describing how the work will be done. So first of all then, to justify why the work needs to be done, you've been given the sufficient background information in a list of 6 statements. By putting them in the correct order and thinking about them, you should be able to come up with a justification as to why the work needs to be done. To help you a little further with that, you need to think even wider than these statements. You have to think, why would anyone want to do any work on contamination? Ultimately, the reason for doing such work is to try and remediate the situation. Much of the work that you're going to do as environmental scientists is going to have that as the primary underlying goal, and it's important not to forget that. So you have to make a link through to remediation in the end. So if we use these statements, you've just been asked to put them into the right order, which I'm going to leave you to do, but I can add a little bit more information about these notes. The first one's description of site and geographical context. That's a note referring to the description of the site, which isn't the site of Paris Mountain. It's the general location of northwest corner of Anglesey in relation to other sources of contamination. The geographical context is the Irish Sea. The Irish Sea is surrounded by major urban and industrial conurbations, which generate contaminants. In this case, particularly interested in metals, but metals are generated as road runoff, also from industrial processes, and they are in fairly high amounts because the population density is quite high around this corner of the Irish Sea. The site we're talking about is the Irish Sea, and the geographical context is the major urban conurbations that surround the coast of the Irish Sea. Paris Mountain was the largest copper mine in the world in the 19th century. The site is now largely abandoned and subject to no controls. Metal burden of the Irish Sea is known to be near EC, that's European Community. Actually, more up to date really, it should be EU, European Union. European Union limits. There's high metal concentration in the Afon-Gok, though low discharge. And the metal flux from Paris Mountain exceeds that of the major rivers of the northwest. That final point obviously is related to the first point. The metal flux from Paris Mountain exceeds that of the major rivers of the northwest. The major rivers of the northwest are those that are actually draining the heavily urbanised catchments. Those rivers are the Dee, the Mersey, the Ribble and the Wyre. There's other smaller ones as well, but they're the major rivers. And the statement is saying that the amount of metal per second that's coming down the Afon-Gok from Paris Mountain is larger than the amount of metal per second coming down the Dee, the Mersey, the Ribble, the Wyre, and entering the Irish Sea. So if you put those points in a reasonable order, and the order should start with the most general point and work through to the most specific, then there should be an aim for this work. The aim is effectively the same as the title. The aim is to determine the extent to which coastal waters are contaminated by drainage from Paris Mountain, Anglesey. But the question still remains, why do that? You've got those 6 points, if you put them in the right order, It gets you very close to saying why you might do that, but you need to explicitly say why you'd want to find out whether the coastal waters are contaminated. And as I said at the start, ultimately the reason for that has to be to do with remediation. How would knowing whether the coastal waters are contaminated by drainage from Paris Mountain, how would that help you in planning your remediation, given what we've said about these very high metal fluxes? And the fifth point, that there's a high metal concentration but a low discharge. And when we say high, we mean high compared to the sum of the metal fluxes from all the other major rivers of the northwest. The question that I would put to you is, if you were tasked with reducing the metal burden in the Irish Sea, which we know is near EU limits, what would be the most efficient? That would be, what's the cheapest way of doing it? Is it to try and control all the discharges in all the major urban centres around the coast of the Irish Sea to stop them getting into the rivers? Or is there another way? If there is another way, then how does that link into determining the extent to which coastal waters are contaminated by drainage from Paris Mountain? So you should be able to state an aim then. You can see that there's actually 3 marks for the aim. There's only 2 for putting those points in order, because that's not that difficult. But the jump from being able to state the argument made in those 6 points through to actually being able to state the aim of the work, and the aim, as I said, is to determine the extent to which coastal water is contaminated by drainage from Paris Mountain, making that link 3 marks. So subsequent to stating the aim, standard section that you'd expect next in a scientific paper is one that would explain how you're going to achieve the aim. So there's something that's worthwhile doing. How's it going to be done? In almost all cases, there will be a section that's required there to break down that overall aim into how it's going to be done. On occasion, it may be the case that once you've stated what the aim is, it's quite obvious how it can be done. This seems like a fairly simple aim, but actually it's not as simple as you might have first thought, and there is a requirement to have the specific introduction which breaks it down into objectives. So ultimately what we want after writing the specific introduction is to be able to state objectives, which are the things that will be achieved in order to make the achievement of the aim possible. What might help you to think about this is thinking what you need to write here is to explain why it might be difficult to achieve that aim, and then explain how those difficulties will be overcome. So if we are trying to survey whether coastal waters are contaminated, what's difficult about doing that? Why is it difficult to determine whether coastal waters are contaminated? There's some guidance here, because we've broken it down into actually producing an argument as to why you have to monitor in a particular way, and in fact why you have to use biomonitoring. And there's a set of points there, again, that need putting in the right order, and by doing that they'll actually show why it's difficult to achieve the aim and how those difficulties will be overcome. So to explain the points again, which again are things you need to put in order, but to explain the points, the matrix effects resulting from the salt content of seawater make spectroscopy inaccurate. Well, 2 things that you may not know about there. Spectroscopy is the standard method of analysing metals in water. It's effectively shining light onto a metal solution and seeing which light is absorbed and which light is emitted. You'll have seen it if you've done a flame test at school, where you can introduce some calcium solution into a flame and the flame turns red, or a copper solution and the flame turns green. They're the characteristic emissions of light that happen when energy is input into a copper ion or a calcium ion, and a spectroscope is a more sophisticated way of analysing those colours. So spectroscopy is the method that's usually used for determining the concentration of metals in water. The matrix effect is the effect of, in this case, the salt. Seawater has got a lot of sodium chloride in it, and the sodium metal, actually the colour that's produced by the sodium, or the light emissions by the sodium, or the light absorbed by the sodium, can actually swamp the light emissions or light absorption from the low concentrations of other metals that are present. So that's the matrix effect. Sodium chloride is the background matrix in your solution. The solution, we're interested in copper in the solution, but the matrix of the solution has got a lot of sodium in it. So seawater, the salt content, makes spectroscopy inaccurate. Biota provide an integrated sampling, saying that if you have organisms that live in the sea, then they sit there accumulating metal all the time, and therefore you get an integration of the metal concentrations. Another one of those points is that metal concentrations in water change with tides and currents. So the concentration of metal might change with tides and currents, but the biota that's present in the water integrate those changes. So they don't vary with the tides and currents. The concentration within the organism is buffered, if you like. It doesn't change with every tide and with every change of current, because the concentration is building up slowly over the time that the organism's in the water. So you have an integrated record. It averages the concentration for you. Biota may concentrate metals, making them easier to detect. You're aware of that. The biomagnification that may go on. It's one of the things you'll have covered in the first year or in school. The salt content of a digest is lower than that of seawater, so reducing the matrix effects. If we take a sample of biota and we dissolve it in acid, and then we dilute the acid with deionized water, that will be the fluid that we actually analyse by spectroscopy. And the salt content, the sodium content, the sodium concentration in that digest is much less than the sodium concentration that you'd have in seawater. So the matrix effect is reduced. The final point is the metal content that's measured in the biota is an indicator of bioavailable metal. The metal that gets into the organism is metal that can get into an organism, and therefore it's the type of metal that we need to be concerned about. Some metals aren't bioavailable, so we might measure them if we were to analyse a water sample, but they wouldn't pass into an organism. By looking at the metal in an organism, then we know we're only analysing bioavailable metal. Now, that's 6 points again that have been explained to you. You need to put those in order. You can see that certain of those points occur as pairs. Well, there might be a problem and a solution. So there's a pair, one problem, one solution. So you need to carefully think about the structure of the paragraph that you're going to write. And you need to think overall what the structure of the paragraph should be. There should be a structure to the paragraph and a structure to each sentence. The starting point for your paragraph really should be to consider what are the problems and then what are the solutions. There's two kinds of problem. There's problems with sampling and problems with analysis, and you should separate these points into problems with sampling and solutions to those problems, and problems with analysis and solutions to those problems. If you do that, you should be able to write a well-structured paragraph that explains clearly what the problems are and how they can be overcome. And that will lead you on then to actually stating the objectives. This is the most critical part, stating the objectives. A lot of thought has to have gone into this. You can start off with something that needs doing, and that's sometimes relatively easy to come up with a justification for doing some work. How you actually achieve it requires some thought. Already you've put some thought in as to the difficulties of determining metal concentrations in seawater and how to overcome those. Now we need to state the objectives. There's still some more thinking that needs to go on here. what we're trying to determine from determining whether the extent to which coastal waters are contaminated, is the Afon Gogh an important source of metal on a regional scale? The reason we're doing that will relate back to your aim. If it were an important source of metal on a regional scale, then we'd expect the concentration of metal to be elevated beyond the point of entry into the sea. So to determine that actually requires two objectives to be met. We need to see whether there's any influence beyond the point of entry. We need to also define what we mean by any influence. So we need to determine two things. What's the distribution of metal around the coast of Anglesey? And we can do that from our own data, from the measurements that we're going to make. But whether those analyses we carry out, whether the concentrations we determine are actually contaminated, whether the samples are contaminated, can only be determined by comparing them to other sites. So we need to make an external comparison as well. So that's why there's two objectives. Because we're doing the two objectives, one to make an internal comparison of data of samples that we analyse from around the coast of Anglesey to see the distribution of the metals and whether they're elevated only at the point of entry or whether there's elevated concentrations away from the point of entry. But in order to say whether they're elevated at all, we need to know what the background concentration is. And in order to find a background concentration, in other words, something that's not contaminated, then we need to look at samples from other sites. So we need to state those two things, two clearly stated objectives, and from stating those, what becomes obvious to the reader is what the methods are going to be. So to achieve the first objective, which is to determine the distribution of metal concentration around the coast of Anglesey, well, the reader's going to expect that you're going to take samples. You've explained already actually that you're going to have to use biomonitoring, but the method is going to involve taking seaweed samples or biota samples in order to analyse them. The other part of the method is to assemble data from other references in order to compare your metal concentrations to them in order to determine whether they're above a background level, and that meets your second objective. We can move on then to the method section. The method section of your scientific paper should contain enough information that the work can be repeated, and it's also there in order that people who read the paper, in order that they have knowledge of the quality of the data. So given what we've been studying so far, this is a very important section. We've identified that we need to control variables apart from the variable that we're interested in, and ultimately the only variability that we want is the variability we're interested in and the inevitable variability that we can't control, which is the variation due to random factors. If the only variability we can't control is that due to random factors, then we're safe to use the parametric statistics that we've looked at so far, recognizing that the objective here, our first objective, is to determine what the distribution of metal is around the coast of Anglesey, and that means saying, is the concentration of metal higher at one place than another? In order to say whether it's higher at one place than another, we need to be able to state that with some level of confidence, which is what you've been working on. So you'd expect to use the standard error and to draw an error bar on the sample sites where you've taken samples and you've measured the concentration. You'd expect to have an error bar on that so you can compare one site with another to see whether the concentration is different. Now, for you to use the standard error, which is derived from the standard deviation, in order to draw your error bars, then it's only relevant to do that if the variability is caused by random factors. We've covered this before. So we need to design our investigation so that the only variability that we're left with is variability due to distance. That's what we're interested in, and all other variability is controlled, apart from the uncontrollable variability, that's variability due to random processes. The method, you're describing how the seaweed samples were taken. We've got 4 points there. You need to turn those into an argument explaining why this method was adopted. All the samples were taken at the same stage of the tide. Only the tips of the plants were taken. Only one species was used, and replicate samples were taken at each site. Now, that's what you need to know to repeat the work, but actually you need to write that out in order to explain why those things were done as well. The variation that we're interested in is the variation in metal concentration due to distance away from the source being the Afon Gok. You have to then consider what else could cause variation in metal concentration in a seaweed. The thing that you need to consider is the exposure of the seaweed. So, one, how long has it been exposed to water containing metal? That'll depend on its position on the shore. If it's high up the shore, then it's not covered by the sea for a large part of the time. If it's further down the shore, it will be. So there's a requirement to remove that variation. If the seaweed's not very old, it won't have been exposed to metal for very long. If it's old, it will have been exposed for longer. How do we control that variation? Well, there's a list of things that you've done there. Which is the one that allows that to be controlled? The amount of metal that's absorbed will be different between different species. Some of them will take up more metal than others. So how do we control that variation? Then, once the variation due to exposure is controlled, then we're left with variation that is a result of distance from the source, but also variation due to very slight genetic differences between seaweed of the same species. We're all of the same species, but we're actually all slightly different to each other. In the same way, the seaweed can be the same species, but it will behave slightly differently. We can't control that unless we spent an enormous amount of money, and even then it may not be possible. We'd have to have genetic clones that we'd have to install at the sites, and it starts to be maybe not impossible, but hugely expensive. So the slight genetic variations, we're going to have to hope that those are actually effectively random. Similarly, whether the seaweed is behind a rock or on top of a rock, assuming it's got the same exposure, it's got the same height on the shore, but it could still be in a slightly different micro-topographic position from one piece of seaweed to the next. And again, we can't control that. Again, we could if we spent an awful lot of money and made particular micro-habitats. So there's a possibility of controlling, but again, it might not be possible. But that variation we're throwing into the pot of random variation. Given that that's a reasonable thing to do, then what do we do if we recognise that it's not possible to remove all of that variability and we are left with this variability due to random factors? We need to take multiple samples. Why do we take multiple samples? There's 2 reasons for that. I'm not going to go into those again because you know them very well, but it explains why you're taking replicate samples. So for that method section, you need to have a structured paragraph explaining that the method was designed to control variation resulting from, explain what the variation resulted from, and how it's controlled. How it's controlled you've got written down. And there's 6 marks there for that structured argument. Then you've got the results. The results are the concentrations, the metal concentrations in the replicate samples at each of the sites. The sites are numbered 1 to 8. We're not interested in numbers 1 to 8. They could be called different names of people for all we care. It doesn't mean anything to us. We're interested in the distance between the sites. So you need to fill in a column that gives you the distance between the sites. Any relationships we want to look at aren't the relationships between site 1 and site 5. We're interested in the distance between them. So you can measure the distance off the little sketch map. You don't need to do it with any great resolution. Just roughly measure the distance off the little sketch map and you can write a column for distance. You need to transfer these numbers into Excel. Write a column for distance, and then you've got these columns to fill in the average and the error, because they're the things you're going to want to know if we're going to determine whether or not there's a difference in metal concentration between these sites that could show us whether the metal concentration is having an influence beyond its point of entry. You can see from the map that the main Afon Gogh enters at site 3. There's also some drainage from Paris Mountain entering at site 6. You need to work out the average and the standard error, and then plot a graph with each of the sites concentrations with an error bar drawn on them, and the x-axis should not be numbers 1 to 8. The x-axis should be distance. And a reasonable thing to do is to just turn this coastal transect into a straight line and plot the concentrations. You can go from site 8 to site 1 or 1 to site 8, but with the distances between them accurately mapped onto your graph. And then from that you can see what the concentration, the distribution of concentrations is. It may be that the concentration is the same all the way around because the error bars might all overlap, or maybe they won't. You need to look. That's the figure that you need to produce. Producing the figure will need a figure number. If you've drawn a graph of this data, then we don't need to see this data table. So it'll just be reproducing the same data. We don't need to see that. So just have the figure. Figure legend should start with a figure number so you can refer to it when you write your results section, and also should make a note in the figure legend that the errors are drawn at 95% confidence. The y-axis on your graph, you can tell from these numbers, in some cases it's 100 times higher the concentration at site 3 than at some of the other sites. So you're going to have to consider the scale that you want to draw the graph on, and that's an important, very important question. It's not a trivial question as to what scale should you draw the graph on, because if you draw the graph running up to 700, whatever the mean of the concentration is at site 3, then it'd be difficult to make out the error bars on the lower concentrations. The question is, are we interested in seeing the relationship between the error bars on the lower concentrations? Do we need to see them, or is it more important that we can just see that you've got a very high concentration at site 3? And you need to answer that by considering your objectives. One of the things I would say is we're interested in the relative relationships of the concentrations at each of the sites. That was our first objective, but we're only absolutely interested in concentrations that are above background. So in order to determine your background concentrations, you've got these examples So if you were to draw a line across your graph, which you could say was the industrial background, then if all the points are well below that industrial background, then we're not really that bothered about seeing the errors on them. You need to put together these two bits of information in order to draw the most appropriate graph. You may find that it's appropriate to draw two graphs, but you should decide on that. The results section then is going to contain your figure with a figure legend, with a figure number, because you're going to refer to the figure. And when you need to write some text in your results section as well. It's not just the figure. You need to pull out the important points from the figure. Effectively, everyone's in a hurry. I don't want to look at your figure if I don't have to. If I don't believe you, I'll look at the figure. But you tell me what the important points are from the figure. And the important points are not that it's gone up here and gone down there. We don't want to describe the figure. The figure's there if we want to look at it. The important points are those that are going to relate to your objectives. You set two objectives. You ask two questions. One of them is answerable from this figure. But you might need to also refer to this data as well. So pull out the points that relate to your two objectives. The discussion section is going to be fairly short because the questions you set up are really directly answerable from the results section. What the extra thing that will go in your discussion is movement towards further work. What are the implications? Okay, the discussion should contain explanations and implications. In this case, there's not much required in terms of explanation. You're just answering the objectives that you set, these two objectives. But what are the implications of that with regard to your aim? And what should the further work be? There should be some further work because you haven't got a complete answer to what you set up as your aim.